Welcome back in the sixth video in the series about multivariate calculus. In this video, we're just going to give some basic concepts about the tensor calculus. Tensor calculus is the study of how tensors change over space. But what exactly are tensors? There are many definitions, but one way of thinking about them is that they are containers that describe data or physical entities in n dimensions. So they can be represented by grids or of numbers, and we can call them n-way arrays. These tensors are characterized by their rank. The rank indicates the number of indices needed to describe them. So this one drawn, for example, is a rank 2 tensor. Another tensor can be rank 1, rank 0. So example being a scalar, so just one entry. Another example is vectors, so rank 1 tensors, because there is a one dimension, let's say. Rank 2 is matrices, as we saw already in the figure, and this is a rank 3 tensor that is not a matrix. We can visualize it as a cube, but yeah, it's not exactly a matrix. It's a matrix of matrices in a way. We can have some operations with tensors. First we define addition. So tensors that have the same rank can be added together, and to have the sum of them, we just add every component in a similar way to which we perform addition on matrices. Then we have multiplication. Tensors can be multiplied using various cooperations like dot product, outer product, and tensor contraction. We will see now the differentiation of tensors. So we can differentiate them, but with different operators. We can take the divergence, or we can have the gradient. We will see on the next slide how to take the divergence of a tensor. We can also integrate tensors, and this allows us to compute quantities like the total flux or total mass, depending on which kind of tensor we are integrating. So, for the divergence of a tensor, we can define some vector operator. We defined in a previous video the del operator for 3-dimension space, but to generalize it in a n dimension, we have del subscript I, defined as EI, that is the ith basis vector, with the derivative towards the ith component, let's say, of x. Then, in matrix form, the divergence of a tensor of a second order and with 3 dimensions, that is the most familiar to us, can be seen in this way. Here we see the del operator for 3 dimension, and this one is our tensor. In this case, we see that the result obtained after applying the divergence is not a vector but a scalar, while every time we would apply the divergence to any vector field, we would obtain a scalar. In tensor calculus, we generally distinguish between covariant and contravariant tensors. Contravariant tensors transform inversely respect to the coordinate system. If we have to take a projection, in the contravariant case, this would be parallel to the E2 cap and E1 cap that we chose, and this would be the formula. While if we have a covariant tensor, the transformation would be in the same way as the coordinate system, and projection would be perpendicular. So in this case, the projection would be in the yellow line, so perpendicular to the two vectors directions E1 and E2. So this was the green one. and this is the yellow one. The transformation of tensors is governed by tensor transformation rule, and these rules ensure that the physical laws remain invariant under coordinate transformations. In general, there are many applications of tensor calculus. For example, in general relativity, tensors describe the curvature of space-time and the behavior of gravitational force. In fluid dynamics, tensors are used to represent stress, strain, and fluid flow. Additionally, there's also tensors like the Maxwell stress tensors used in electricity and magnetism. This is just a picture of a rank-free tensor. And with this, we end the last video of our series about multivariate calculus. I hope you enjoyed it, and let me know if there is any question. Just for information, these were the references used for the slides, and with this is really all. Thanks for the attention, and goodbye.